Hi everyone, I am Sayam Galotra. Today I am going to present our work on hierarchical entity resolution. This is joint work with Donatella from Sapienza University, Barna from University of California, San Diego, and Devesh from AT&T. As we all know, large amounts of data has become easily accessible on the web. However, this decentralized supply of data has introduced numerous challenges. For example, data is available in different formats like CSV files, images, unstructured text, tables, and so on. There are a lot of duplicates contributing to the redundancy of information available from different sources. The sheer scale of the datasets make it further challenging to clean and organize them. Now let us look at a simple example from e-commerce domain. This is Bob, who owns a store that sells beverages. And one day, he decides to set up an online store so that people can buy products online. Now, Bob goes on to Amazon and really likes how different products are organized. Specifically, he likes that a type hierarchy allows users to navigate through the products, and other seller information combines all duplicates into a single location. Now, Bob wants to organize the products that he has in his store. So what he does is he goes over all products, takes a picture of every beverage and creates a table with title, price, brand information, and the pictures. Now, Bob has a list of all products that he wants to show on his website. To organize the website, he manually comes up with a hierarchy and assigns each product to a category in that hierarchy. With this hierarchy which he has set up, the website, he's not very happy because there's some duplicates which are spoiling the search results. He also notices that his organization does not distinguish between caffeinated and non-caffeinated drinks. He then goes back and modifies his hierarchy to add these additional categories. After spending all this effort, he realizes that he missed organizing the instant coffees into spray-dried and freeze-dried instant coffees. And he has to again go back and modify the hierarchy. By now, you may have noticed that manual curation of this hierarchy requires a number of back and forth updates, which means checking all products again and again to ensure all categories in the hierarchy are correctly identified. Also, it requires Bob to constantly keep track of all types of product categories as products evolve over time. Now, let us look at the ideal organization for these products that would have made Bob happier in the first place. In this organization, parents of leaf level nodes are the entity nodes which identify duplicate products. So any pair of records which share the parent at the leaf minus one level are duplicates. And all other nodes are categories that are organized based on type subtype relationships. Generating this organization of records is quite challenging. If we try to do this manually, we need to go over all products again and again. It requires the individual to keep track of all categories and its variations. In contrast, building an automated approach is also challenging because of presence of noise and missing information in record descriptions. For example, herbal tea does not mention the token non-caffeinated drink anywhere in the description. So inferring that non-caffeinated should be a category is very challenging. Similarly, the token hazelnut in hazelnut coffee is a flavor and not a nut. Developing automatic techniques to make this distinction is quite challenging. Now, if solving the end-to-end problem is very difficult, how can we proceed? In this work, we consider an oracle to help us with the construction. An oracle does not solve the complete problem end-to-end, but just looks at a small sample of 2 or 3 products and answers simple questions. Specifically, we consider 2 different types of oracle in this work. First is a pairwise comparison oracle, which answers a simple yes-no question to check if the 2 records refer to same entity or not. In addition to a pairwise oracle, we consider a triplet oracle, where the goal is to find an odd one out. Oracle is given 3 records, and it outputs 1 record, which is the farthest from the other 2. The 2 different types of oracle that we consider can be implemented by showing such questions to Bob, or to a crowd worker, or to a machine learning model trained over the dataset. The key reason to consider an oracle is that each question is considered in isolation, and the oracle can just look at those input records and not the whole data set. With this, let us define the problem statement. We are given an input collection of records and an oracle that answers both pairwise and triplet questions. Now, we want to organize the records in the form of a hierarchy that captures type subtype relationships and duplicate relationships between records. In this process, we not only want to make sure that the number of oracle queries are minimized, but we also want to identify as many relationships as possible early on than later. For example, consider the graph that denotes F-score versus the number of queries curve for 4 different techniques here. In this graph, black and green curves are definitely performing good because they reach perfect score before red and blue. However, green curve is faster in identifying more relations and has higher gain in F-score early on. Considering this growth of the function in the optimization is very important for building an anytime algorithm. Uh, to capture these differences, we use the notion of progressive F-score, which is characterized by the area under the F-score query curve. In this example, green curve has the maximum area under the curve, and that is why it has the maximum progressive F-score. Now, before discussing our approach, let us see how we can adapt prior techniques to solve our problem. There is no prior approach that solves the organization problem discussed before completely. However, there are some techniques that solve the problem partially. For example, prior oracle-based entity resolution techniques consider a pairwise oracle to infer duplicate relationships. But these techniques do not organize them in the form of a hierarchy. There are some recent techniques that have studied taxonomy construction, where the records are organized in the form of a hierarchy to capture type-subtype relationships. These techniques do not capture duplicate relationships and are designed for the case where the hierarchy is guaranteed to be binary. However, most of the real-world hierarchies are not binary, and extension of these techniques to non-binary hierarchies has poor query complexity. These two types of techniques can be used together to solve our problem of not only identifying duplicate relationships, but also organizing entities according to type-subtype relationships. This brings us to the first baseline, which first runs entity resolution over the records to identify clusters of records that refer to the same entity, and then perform taxonomy construction on top of these identified entities. One of the main disadvantages of this approach is that it compares many different record pairs, which are non-matches, before identifying any type-subtype relationships between them. Secondly, it uses prior taxonomy construction techniques which were not designed for non-binary hierarchies, and therefore they have suboptimal performance. An alternate strategy would be to run taxonomy construction first and then post-process the hierarchy to identify duplicate relationships. This approach also suffers from similar challenges as discussed previously. To handle these challenges, we propose an adaptive approach that simultaneously identifies duplicate relationships and type-subtype relationships between records. The architecture of our approach is shown here. In this architecture, the red-colored boxes are the components proposed by us in this work, and other components are adapted from prior literature. At a high level, blocking is performed over the input records to identify a small set of candidate pairs, which are used by the subsequent stages of the pipeline. The blocked pairs are then used for similarity computation and initialization of the higher ER approach. The initialization component uses record pair similarities to construct a rough taxonomy of records using an automated hierarchical clustering technique. This taxonomy is used as a guidance for the Oracle strategy. The Oracle strategy prioritizes records based on scoring mechanism and adaptively identifies queries for the Oracle. The Oracle response is used by the inference component to organize the queried records in the form of a hierarchy. I won't go into the details of our approach, but will quickly present the key ideas behind the Oracle strategy. The Oracle strategy stores a set of processed records and maintains a hierarchical representation over these processed records. The records are processed in decreasing order of expected gain, and the Oracle strategy adaptively chooses the type of question asked based on a benefit notion. Benefit of a product U with respect to any location V in the hierarchy is defined as the expected gain in recall when U is attached to V. Here we show a simple example where the probability of attaching the record 4 to this internal node V is 0.03, and the gain in recall if we attach 4 to V is 1.56. So the benefit of attaching 4 to this location is the product of these two terms. In addition to the Oracle strategy, we analyze the theoretical guarantees of our approach and prove that it can construct the hierarchy in order of n log n queries under reasonable amount of noise. Now let us look at some evaluation results. We considered 6 different hierarchies from varied domains like phylogenetic trees, e-commerce hierarchies, DMOS, and geographic. All these hierarchies have different depth, average degree, and shape. Here is an example hierarchy for phylogenetic trees, which has very high depth and is mostly binary. Now let us compare the results. In this result, we compare F-score versus the number of queries for 4 datasets. The blue curve is the higher ER approach, and the black curve is an ideal approach, which denotes the empirical lower bound for each dataset. As compared to baselines, higher ER is always closest to the ideal curve. In fact, other baselines like insertion sort and hybrid have a very poor progressive growth of F-score. Approaches like average link and high XPAN initialize the hierarchy based on similarities and therefore start with a non-zero F-score. However, these techniques are not able to improve upon the initial hierarchies by asking more questions. In summary, we studied the problem of organizing records in the form of a hierarchy that captures is a type, subtype, and duplicate relationships. We leveraged the notion of an oracle to generate a hierarchy and used benefit-based approach to prioritize queries in such a way that it optimized progressive F-score. Experimental evaluation on various real-world datasets demonstrates the effectiveness to generate the hierarchy. Thank you.